Welcome to Mathema by RC YouTube channel. This is our lesson 12 of class 10 of the class chapter real number. In this class we summary that the chapter of real number in this summary section. In this chapter we have studied the following points in this previous classes. So we look out at a glance that in this real number chapter what it have had and how we can complete this chapter. In this chapter we have studied the following points: Euclid's division lemma. We already discussed Euclid division lemma, that the given positive integers a, b, there exists a whole number q and r, that means the quotient and the remainder satisfying a equal to bq plus r, where the condition is r greater than equal to 0 less than b. Okay, so the given positive two integers a, b, there exists a whole number, there exist the whole numbers q and r such that a equal to bq plus r, where r greater than equal to 0 less than b. Euclid's division lemma, this is called the lemma, and Euclid's division algorithm, this is the base of the Euclid's division lemma. According to this HCF, that means highest common factor of any two positive integers a, b, where a greater than b, obtained by this following part by using the Euclid's division lemma. First, apply the division lemma to find q and r such that a equal to bq plus r from the Euclid division lemma, r greater than equal to 0 less than b. If r equal to 0, then HCF is b. If r not equal to 0, apply Euclid's division lemma to b to r. So in this step 2 we already discussed, if r equal to 0, then b divided by a divided by b. So b is the HCF of a and b. But if r not equal to 0, then we use the Euclid division lemma for b and r. Continue this process till the remainder is 0. So continue this process till the remainder 0. The divisor at this stage will be HCF. That means when we get the remainder 0, the divisor, that means the divisor of, in this stage the divisor of HCF and divisor of the stage is the HCF of a comma b. Also HCF of ab equal to HCF of br. Here we use the another theorem, that means it is called fundamental theorem of arithmetic. That means every composite number can be expressed as a product of primes, and this factorization is unique when we use it. It is an order, that means it is an descending order or ascending order. Okay, so every composite number can be expressed as a factorized as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. Okay, if p is a prime number, p divides a square, then p divides a. P is an positive integer. So if p is a prime number, p suppose a prime number, and p divides a square, suppose p divides a square, then p also divides a. Okay. Suppose to prove, we also prove root 2 and root 3 are irrational numbers. That means by contradict that root 2 and root 3 are not irrational number, we get a contradiction. So we also solve this portion, root 2 and root 3 are the irrational number in this previous class. You can also see in our YouTube channel playlist. Here we get the root 5 minus root 3 is an irrational number. Also we use here root 2 is an irrational number. Okay, so you can see all the classes in our YouTube channel for free. Okay, and anytime, anywhere you can get this class. So in the 6, let x be an rational number whose decimal expansion is terminates. We know that the rational numbers can be represented in decimal expansion, and the rational numbers can be represented in decimal expansion and also we get two types of two cases here. One is the terminates, another is non-terminating but recurring. So then we can express x as a p and p by q form. We also know that all the rational numbers can be represented in p by q form, where p, q are integers and co-prime, and the prime factorization of q is in the form 2 to the power n and 2 to the power m, where mn are the non-negative integers. When we represent q as a 2 to the power n and 5 to the power m, then we note that the prime factorization, the decimal expansion of this prime factor, the decimal expansion of this p by q form is terminates when we express q as a part. Here we also discuss in this class. Here you see that the theorem, okay, the theorem 1.5, 1.6 and 1.7 here, okay. In this next part we also discuss that when p by q are rational numbers such that the prime factorization of q are in the form 2 to the power m and 2 to the power n, where mn are negative, then the x is decimal is terminated. Therefore, the 6 and 7 are the reverse process. So when it is an rational number, decimal expansion terminates, then we represent q as a 2 to the power n and 2 to the power m. Also, when we see that in p by q form, q is a 2 to the power n and 5 to the power m form, then we also note that the decimal expansion of this rational number is terminates. But if p by q form be a rational number such that the prime factorization of q are not in the form 2 to the power m 2 to the power n, mn are the non-negative integers, then x has a decimal expansion which is not terminating and repeating and recurring. So if you not this portion cannot then we get the not terminating and recurring decimal expansion. So you get all the theorems and all the main points in the summary part, and also you can see the previous classes. Here we get the 11th class, 10th class. Here we get the theorem 3 theorem in 9th class. Also you get 8th class, for example 5 minus root 3 is an irrational. You get 7th class, root 2 is an irrational. LCM and HCF, find out the LCM and HCF of this number. We also find out the prime factor of the product of primes, that means HCF and LCM. We get this portion likewise, okay. So please subscribe our YouTube channel, stay with us for this next class, next chapter, and join our Telegram group. In the description box you get the link of this Telegram group, and like this class, share with your friends. Thank you, stay with us. Thank you.